Howdy there. The purpose of this video is to take you through how to do the elevator lab, which is a little bit of a different lab because we can't do it within the school. We certainly can't do it with the little elevators that we've got in the school, at least, because we need something that's going to go through a bit more of an acceleration. So that's what I'm going to try to outline for you here, is how you're going to go about doing it when you're not inside the school. So one thing that you do have to remember is that this is a group lab. There will be no solo labs accepted. You are supposed to do this with between 2 to 4 people in total in your group. And it's really actually quite necessary because one of you is going to act as what we refer to as the test subject. You're going to be the person that's actually standing on a scale so that we can see differences in your mass while the elevator is accelerating. It is actually difficult to really catch those changes in mass if you're standing up on top of a scale looking down. You're going to need somebody that's going to be the minimum other second person in the group that's going to be looking down at the dial on the scale to read those changes while the elevator is accelerating. So the objective of this lab is to measure the acceleration of an actual elevator as it both rises and descends. So one thing I'm going to point out to you more clearly later is we are measuring 2 different values here. One for going up, accelerating, faster, 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 positive acceleration, and one while it's coming down, negative acceleration. Those are going to be 2 separate numbers, and we don't actually have any expectation that they will be the same value. Now, as far as your hypothesis goes, there's no way for you to be able to make some sort of a prediction in advance of an exact number. It would be unfair of us to just make up a number like 3 meters per second squared. But what we can do is make a educated, reasonable guess about maybe even a range of values. Because what we have to consider is that in class we talk about, what sort of things happen when you're going up and coming down on an elevator. One of the things I usually talk about is that on the way up, the human body feels more comfortable with higher accelerations because you feel yourself snugly more against the floor then. But on the way down, people feel very uncomfortable with high accelerations. So usually that acceleration is less, in magnitude at least, on the way down. So you might be able to say something about that as far as a reasonable range of numbers might be. Definitely nothing like 9.81 meters per second squared, because that's either being crushed against the floor on the way up or actually being essentially in free fall. That's not reasonable. You still need to write out formulas in your hypothesis. And remember, in a hypothesis, we don't show how formulas stick together as we would in analysis, manipulations and things like that. You should be showing just the basic formulas that are relevant to your lab. And you do need to still mention your controlled, manipulated, and responding variables. Now, for the equipment list, I just say here, follow the lab template, but the most critical thing, and we're going to talk a little bit more about shortly, is you do have to have a standard bathroom scale. And you'll notice that this one is sort of an old school one with a dial on it. We would call it analog. It is not a digital scale. And that's where we do get into some procedural notes. Realistically, you cannot do this lab with a digital scale. I know they do tend to be more accurate. And remember, the specific definition of accurate is it's giving a value that is closer to a true value. And that's great, okay? Analog scales are a little bit more old school. But the issue with a digital scale is that if you think about how a lot of them work, you step onto them and you got to give them, a couple of seconds before they actually show a reading. And that's not possible for the lab we're doing. We need something like this because right as your mass is going through its apparent changes, this will actually change. It'll shift. And we need to be able to look at it that way. So it might not be as truly accurate, but it is what's necessary for us to perform this lab. Now, a couple other things to remember as far as procedural notes go. You still have to write out a procedure of what you do, but the acceleration of your elevator only truly happens right near the very beginning of the trip up and right near the very beginning of the trip down. Those are the two accelerations that we want you to try to read. During a whole bunch of the motion of an elevator, the elevator actually moves at pretty much a fairly constant uniform velocity. That's kind of the middle of the trip, and we're not interested in that. We want that burst of acceleration at the beginning on the way up and burst of acceleration as we start to come down. That's the acceleration we're trying to measure. And two accelerations. I got to really stress that for you. We want to measure that acceleration when you're on the way up and you feel heavier and your scale will register you as being heavier. And then again, on the way down, when the scale is going to register you as feeling lighter. Now, you do need to choose an elevator that travels through a pretty big distance, a pretty big number of floors, because realistically, if you're talking about an elevator, maybe even if you live in an apartment building where they've got like 4 floors or something, those elevators don't have to accelerate very much because you're not going through a very large trip. So they don't tend to actually be very useful for this. It does mean that you have to have a building with a lot of floors. I would say probably about 10 at least to really get good readings. And you've got to start in the lobby, like on the first floor, saying, oh, set it to go, up to the 10th floor sort of thing, if that's the highest floor there is, and then starting on that highest floor and coming down for those measurements. So that means, typically speaking, office buildings in downtown Edmonton do tend to be better for this. So, this is where if you want to bring your parents, guardians, whoever in and show them this crazy video that I'm making and say to them, see, it's actually my crazy teacher asking me to go downtown. Yep, that's what I'm asking you to try to do. Now, this is because we are doing this for a way to link together the physics that we're studying with real life situations. That's what we're trying to see here. But I do want to also firmly get you to understand that I do not want you taking your scale, hiding it, under your jacket and sneaking into some building downtown and trying to do this in some sort of a sneaky way that tries to get around people or something. No, it's legitimate science here. So if you go to one of those big buildings downtown, a lot of them do have like that information desk at the front, or there might be a security desk or something like that where, somebody sits there most of the time just monitoring the building, basically. Go up to them and politely and, explaining to them, hey, I've got this crazy physics teacher and he wants me to do this lab. I've been doing this lab now for almost 3 decades. And you'd be surprised, there's a lot of people that work downtown that have had my students come up to them previously. And they might say to you something like when you say to them, oh, I'm trying to do this lab, and you bring out the scale and the bill, oh, you're in that physics teacher's class. A lot of them are actually really nice about, yeah, go ahead, ride the elevator, just, don't go crazy, don't ride up and down 73 times, and don't block other people that legitimately need to use the elevator. Don't disturb them. And then they'll usually be pretty cool about it. There's even some people that have gone to do the lab where the security guard type person has said, can I come and watch? And they've included pictures of them with the security guard on the elevator. Maybe ask the security guard if they want to be the person that stands on the scale and becomes your test mass, as long as they have a positive self-body image and all that sort of stuff. So consider that, just be polite and make sure that the individuals that you might be interacting with while doing this are aware of what you're doing, because it is for a legitimate reason. Then, when you get to the elevator, you are going to have to stand on the scale and take a measurement before the elevator starts accelerating. That's quite critical because that is your true mass. You'll be recording that in the observation section. But then I would suggest you do probably at least about 3 trials up and 3 trials down, where you're measuring the apparent mass on your scale that it shows right at the beginning of either part of the travel, where you'll see the scale shifts quite dramatically to being less mass on the way down and more mass when you were on the way up. For pre-lab questions, there's none assigned. In observations, I should see that you have a note of what your true mass is. Make sure that that's there. And then a table of values that shows, like trial 1, trial 2, trial 3 going up and going down, and shows what those apparent masses are that you have. Now for your analysis, hey, good news. You don't have to do a linear regression for this one. But what you'll need to do is some calculations, basically like the ones that we do in class in the examples that we were working through, where you're using your apparent mass and your true mass together to calculate the acceleration of the elevator as it goes up, and that's one set of calculations, and another set of calculations for coming down. Now, I quite often get asked, when do we take averages and stuff like that? You should never do averages until the very end, because the idea is anytime we start doing things like averages, we're rounding things off typically. So if you did 3 trials up and 3 trials coming down, I should see that you have done 3 separate calculations for going up and 3 separate calculations for going down, 3 different accelerations for each. And then you can take your 3 accelerations for going up, average them and give 1 acceleration up. Your 3 accelerations for coming down, average them and give one average value for coming down. So that by the end of all of this, I've got 1 value for up and 1 value for coming down. Now, error, we can't do the typical calculation thing where you're going to say, I'm this many % off or something like that. And we're not even going to calculate like a % difference between up and down, because we don't expect them to be the same, and it doesn't really carry that much meaning for us. So don't worry about doing any sort of error calculation, but you should talk about sources of error. And a lot of that can be things about the scale you're using, but also just think of the experiences you have while you're in the elevator, things that happened that you think actually did legitimately influence the measurements you were taking. In your conclusion, please just do a regular conclusion write-up. And for post-lab, you don't have any post-lab questions assigned. Now, I do expect that there is a chance that beyond me making this video for you, you might have some questions. Please come and see me, ask me questions in person, send me an email, send me a message in Teams if there's anything that you think you need to clarify or discuss, and I can try to help you out with that. So I hope that is everything you needed, and good luck with that.